Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we have 6 integrals to take care of, and we're going to try to use the basic integration rules. Let me remind you what they are before we start. And here we go. We have elementary functions and their integrations known so far. So we have 20 of them involving trig functions, exponentials, and difference or sum of the squares in certain forms. So please have a good revision of this or have it ready with you when you start thinking which one is more applicable to one of those integrals. Okay, so also we have some techniques that we may use along the way. Let me just also remind you what they are. Here we go. There's a list of techniques that uses both algebra and trig. So like expanding the numerator, separating the numerator, completing the square, dividing improper rational function by using long division, adding and subtracting to the numerator of a rational function, or using trig identities like Pythagorean theorems or double angle identities or power reducing formulas. I just listed a few of them here, but there's different versions of that. And by the time I need to use one of those, I'm going to provide you exactly what I'm going to use in the videos. Also, multiplying the top and the bottom of the rational function by the conjugate of the bottom or the top, depending on what the situation is. So make sure that you have like a good grip of those techniques, and there's also an example for each case, so you will actually know what I'm talking about when you look at those cases separately. And have your integration formula card ready together with those techniques somewhere next to your notes, so that when we start solving the problems, you will actually see what I am referring to. All right, let's hit the road. All right, I'm going to start with part A. Part A, we have 4x and 2 over 2x plus 3 quantity squared. So two different types of two different expressions to integrate. And 4x is sort of like easy because I'm going to utilize number 4 as you see here. It's u to the n du equals integrated, u to the n du integrated is u to the n plus 1 divided by n plus 1 plus c. That's power rule for integration. And for the second part of the integral, I am going to use the same thing because apparently if I call the bottom of bottom 2x plus 3 to be u, then I can convert that integral into the form of u to the n du. Okay, so why don't we handle the second integral here first? Then I'm going to combine these two at the end. So first, I am taking care of this integral here. Okay, and I'm going to call u to be 2x plus 3 so that du equals this is dx, right? Sorry. All right, so du equals 2 dx. Okay, that's good because 2 dx pop at the top, right? So this integral becomes du over u squared. In other words, this comes with the negative exponent u to the minus 2 du. All right. And now I have the integral u to the n du form, and I can use the power rule for integration. That number 4 that we just have seen in the beginning. All right. So that is u to the minus 1 divided by minus 1. That's in fact, by going back to the reciprocal notation, minus 1 over u plus c. But the original integral is in terms of x, so I have to go back to the x notation here. Minus 1 over 2x plus 3 plus c is the integral of the second expression here. Okay. So now let's just have the final shot here. That integral 4x minus 2 over 2x plus 3 quantity squared dx is, so 4x is integrated as 4x squared over 2, which makes it 2x squared. And I have the integral of 2 over 2x plus 3 squared given here. that comes with a minus sign, but I have another minus sign here, right? So that makes it, let me just write the full term here. So let's write the full version. But now I have two minus signs, so that makes it 2x squared plus 1 over 2x plus 3 plus c. And I don't have any dx here. That's a typo. Okay. All right, you can put a generic integration constant at the end without bothering yourself along the way. And that's pretty much what the result of the integral in part A is. How about part B? Maybe we can get this sorted out as well in this video. 3x over x plus 4. Why don't you just pause the video and stare at the integral and think about it, and in fact check what type of integral that we can put that in. The interesting thing is that the bottom, you calling the bottom would not help to you because you have x plus 4 in the bottom, and then du is going to be dx, but you still have the x term staying still up there. So so I think the best way to handle this problem is to simplify this rational expression, and I can tell you how we can do this. Okay, so essentially all I'm going to do is I'm going to add and subtract an integer, and this is, by the way, one of the tricks that maybe you can check in the lecture notes or in the ebook. We have the procedures for fitting integrands to basic integration formula, and sometimes you can add and subtract terms in the numerator. So if you sort of like check this condition here, adding and subtracting terms in the numerator, you will understand what I'm talking about. So and this is what I am going to use in here. Okay, so let me just rewrite this expression here. So all I'm going to do here is that I'm going to make it look like 3 times x plus 4 divided by x plus 4, but since this 4 at the top is extra, right? So that's an extra term. That's me making the top looking like the bottom. So there's a payback for that. So 3x plus 12, if you expand it out. So that 12 wasn't there, so I'm going to subtract 12. Okay, so I'm going to subtract 12 at the top. Okay, this way I can split this fraction into 2 fractions. Okay, and here we go. So we have 3 times x plus 4 divided by x plus 4 minus 12 divided by x plus 4. But the very first fraction is simplified to 3, and then the other one is still 12 over x plus 4. That's good news because I can handle, or I can integrate each piece separately, because this is the integral of a constant, and this is something that I can use a u substitution for. So in fact, I can handle that right here. So 12 dx over x plus 4, right? I'm going to call u to be x plus 4, so that du equals dx, right? So this integral turns out to be 12 over u du. Okay, this is one of the known integrals. That's number 5, right? Du over u type integral. That is integrated as ln of u plus c. There we go, ln of u plus c. And u was x plus 4, so putting that back here. So ln of x plus 4, an absolute value, plus c. So that's good because I can go back here. And write this integral in one shot. Let me just continue from here. So the first term was like 3 dx, and then the other one is 12 over x plus 4 dx. Again, we use the divide and conquer technique. So this is 3x, and then the other one is 12. I forgot the 12 here, by the way. Please put that back here.
that you have 12 times ln x plus 4 in absolute value. So 12 ln x plus 4 plus c is what you have in the final output. Again, the whole story here is based on using one of the algebra technique that we had in this table, that adding and subtracting terms in the numerator. Okay, just save this table for your reference for the rest of the question, and I'll continue part C and the rest in the next video.